So now let's move on to module 4. We're going to have to speed run this a little bit because we only have around 20 minutes left for our 2-hour lecture. So let's go through module 4. So let's look at the size of a charge, force, or the force generated by a charge. So like charges repel one another and opposite charges attract one another, but by how much do they repel and attract by? So we have Coulomb's law to denote that. So if we're trying to find the forces between 2-point charges, so they're 2-point charges, right? So let's say I have one proton, one electron, and I'm trying to find the attractive force. I can use Coulomb's law. So in your data sheet, if you look in your data sheet, you should have the charge of an electron in coulombs. So it should be like 1.609 times 10 to the power of negative 19, something like that. And we have the charge of a electron, which is also 1.609 times 10 to the power of negative 19, something like that, right? So we have the charges of an electron and a proton in coulombs. So we have, by finding the distance between the two of them, between that electron and the proton, we can now find the force of attraction between the two. So that distance is going to be r, the radius squared. We have the charges from the data sheet. Using that, we can find the attraction between a proton and an electron, the force of attraction. So we use Coulomb's law. So this E over here, this epsilon over here, that is a constant that you have on your data sheet as well. So not to worry about this constant over here. So this white value is a constant. It's given to you. The black value is the magnitude of charges and distance, which determines the force. So this is Coulomb's law, which we'll use to find the magnitude of the forces between 2-point charges. And we also have two means of charging something. So we have charging by friction and we have charging by induction. So charging by friction is where we transfer electrons from one object to another by giving it static charge. We just rub something against another object and then we give it static charge. Charging by induction is where we charge without contact. So it involves an externally charged object and a ground wire, basically. So let's go through the points of, let's look at this now. So this is like, the electric waves generated by a point charge, 2-point charges, right? So if they are, let's look at if they are, they're like charges. So if they're like charges, you can see that they repel one another from these electric field lines. You can see that they repel one another. And using Coulomb's law, we can find the magnitude of repulsion between these two like charges. Now, if we look at these two unlike charges, you can see that through the electric field lines, they attract one another. And so using Coulomb's law, we can find the force of attraction between these two unlike charges using this formula over here. Now let's look at charging by friction. So charging by friction is if I rub like one object against another object, I'll deposit electrons onto that second object to give it static charge, basically. So that's kind of what charging by friction looks like. Charging by induction, that's this diagram over here. So I have a metal sphere. Let's remove this ebonite rod. Let's take this ebonite rod away from the equation. I have a metal sphere, right? Metal sphere will have positive and negative charges mixing around. Well, not positive charges mixing around, mainly negative charges mixing around. And by negative charges, I mean electrons, because metals have free-flowing electrons. So these electrons will be moving like randomly throughout the metal. And now let's take an ebonite rod. So I'll take an ebonite rod, which is negatively charged, place it near the metal sphere. Now what will happen? Well, like charges repel, right? So these free-flowing electrons will now move to the opposite side of the metal sphere, away from the ebonite rod. And so a negative charge or a negative polarity or negative dipole will be generated on this side of the metal rod or the metal sphere, which is facing away from the ebonite rod. And because negative charges accumulate here, respectively within that metal sphere, a positive charge or a positive dipole will be induced at this area, which is next to the ebonite rod. So now all I have to do is, because I've separated the positive and the negative charges respectively within the metal sphere, all I have to do is I now have to siphon off all these electrons to make the metal sphere positive, right? So what I do is I take a ground wire, I connect with a connection to the ground, and I siphon off these electrons that are, now like bundled up in this one corner of the metal sphere or this one area of the metal sphere. All I have to do is I siphon out these electrons using a grounding wire. And I now remove the grounding wire and remove the ebonite rod, and all I'm left with is a positively charged metal sphere because I've removed all the electrons. So I've removed all the negative charges to get a overall positively charged metal sphere. So that's how you'd charge something by induction using a grounding wire. Okay, so now let's look at an electric field. So this is parallel electric fields, the electric field lines between parallel electric fields. So questions might ask you to draw parallel electric fields. It's very important that when you draw them, you make sure that the field lines are equidistant from one another. So the distance between this field line and this field line have to be the same distance as the distance between this field line and this field line. So all these separate this, increments of separation, they have to be equal from one another. The other thing is that it always travels from the positive plate to the negative plate. And the equation that you know to here is the electric field strength within this parallel electric field, or this electric field within this parallel electric plates. The electric field strength here is denoted by E, which is electric field strength, is equal to the force between these two plates divided by Q, which is the charge. Alternatively, it can also get E is equal to negative voltage divided by this distance. So let's look at a moving charge now. So a moving charge in an electric field can be visualized by moving mass in gravitational field. So what that means is, let's take a proton moving through this electric field, right? So let's ignore gravity now. So there's no gravity in the system, only a proton moving like this. What will happen is the proton will be moving like this, and then all of a sudden it'll experience a force that's akin to gravity, right? So it'll experience a force going downwards because it's attracted to this negative plate and it's repelled by the positive plate, so it will attract a force downwards following this electric field lines, and so it will now undergo parabolic motion to reach the ground. Similarly, if I now throw a ball horizontally in a gravitational field, it'll also follow a parabolic motion to the ground. So it's like this, it's like gravity basically. That's kind of what this electric field is like. So the equipotential lines, or the electric field lines, are the lines above, which are like gravity. So these lines over here, and a moving object side to side does not change an object's gravitational potential. Similarly, moving a charge side to side within this electric field plate, or this electric field, does not change its electrical potential energy. So it doesn't change that. It doesn't change that. But when I move an object up and down the equipotential line, it changes my potential energy. So there's a change in my potential energy when I move it up and down these equipotential lines, but not when I move it across, just like for gravitational field lines. And so I can use that to find the voltage. So the voltage is given by the change in gravitational potential energy over the charge of that object. So that's a formula for voltage. I have my formula for electric field lines, electric field strength as well. Same with over here. And if I want to find the force that's generated within an electric field, or this electric field over here, all I have to do is F is equal to QE. So I just rearrange this equation, multiply both sides by Q to get F is equal to QE. So that is electric fields now. Now let's go into electric current. So electric current, right? So current I is denoted as the movement of charge, and it's modeled by the form I over here, which is current is equal to the amount of charge that's moving per time. So the movement of charge with respect to time, Q over T, that's current. And it's measured in coulombs per second, also called amperes or amps, which you might have heard before. We also have voltage. So voltage creates a potential difference, positive and negative end, which is the same as just creating an electric field, just in a closed circuit of wire. So voltage is given by energy per charge, basically energy over charge. That is voltage over here. And we also have Ohm's law, which is the relationship between voltage and current. So we have resistance, which is how difficult it is for electrons to move through a component, and that's measured in ohms. So, and it's also denoted by the symbol R. So velocity, the relationship between voltage and current, is due to R. So if the resistance is very high, then the current is going to be very low, given that voltage is the same. So if I all of a sudden increase resistance and maintain voltage, the current is going to decrease. So yeah, this Ohm's law works for simple resistors, but more complex resistors are non-ohmic, so they don't follow this Ohm's law equation. But for most simple resistors, Ohm's law works. Okay, so now let's look at energy. Energy loss, power, and energy itself. So an ideal circuit, by definition, this is quite important, right? A question can ask you what an ideal circuit is. And to answer that question, an ideal circuit has no energy loss whatsoever. Not to heat, not to sound, not to vibrations, nothing. An ideal circuit has no energy loss. But, in the real world, we're obviously going to have multiple forms of energy loss, right? So if energy is lost in a circuit, remember energy can't be created or destroyed. It can only be transformed or transferred, right? So if energy is lost within the circuit, it's not destroyed, it is transformed, and it's most likely transformed into heat. And this is a result of non-ideal efficiency. So In real life, we don't have ideal circuits. We always have energy loss, and that's due to energy most likely being transformed into heat. We also have equations for power, which is measured in watts, which we did talk about earlier. So we had 150 watts for our previous question, if you think back to earlier. And the formula for this, or to find power, we can do voltage times current, or voltage squared divided by resistance, or current squared times resistance. And many variations are when we substitute Ohm's law to find power. So we have VI, and we substitute V equals IR to get these many variations in. Let's look at energy now. So a circuit component such as light bulb will take electrical power over time and transfer it into light and heat. So we take electrical power and change it to light and heat. So energy is equal to power times time. So PT, which is equal to joules, which means that a watt is just a 1 joule per second. So watt is just energy over time, which is, power. So power is given in watts. So watts is just energy per time. So it's in essence just 1 joule per second. 1 watt is 1 joule per second, which is, if you think back to that previous question, it's also Q over T, because Q is in joules, T is in seconds. So Q over T is joules per second, watts is joules per second, and it all ties into this formula over here. That's pretty cool. So now let's go into series and parallel circuits. So we have a series circuit over here and we have a parallel circuit over here. What's the main difference? So we have two resistors on both. What's the main difference? Well, in a series circuit, if I go through this entire circuit now, I don't need to take, there's only one path for me to take, and in this singular path, I go through both resistors. Now, if I go through a parallel circuit, I reach this point where, this dot point over here, where there's two paths for me to take, and I'll hit, and whichever part I'll take, I'll be exposed to a different resistor. So that's kind of the difference between a parallel and series circuit. And to find the resistance within the entire circuit, to find V equals IR for the whole circuit, we need to simplify it, right? We need to simplify this resistance into one simple resistance to find to apply Ohm's law. So we can simplify the resistance by finding the total resistance in the circuit by doing R total, or R EQ, is equal to resistance 1 plus resistance 2 plus dot 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 plus the amount of resistors that we have. So in this case, we have two resistors, so I'd add 100 plus 200 following this equation to get 300. So now I've simplified this and I can now use Ohm's law in this circuit. These are we can also do the same for parallel circuits. So in this case, 1 over the total resistance is equal to 1 over resistance 1 plus 1 over resistance 2 plus dot 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 for the number of resistors that we have. So in this case, I do 1 over total resistance is equal to 1 over 100 plus 1 over 200, and then I divide divide that entire thing to get 66.67 as my total net resistance within that circuit. That's the difference between parallel and series circuits. So have a go at remembering this formula over here for series and parallel circuits to find the net resistance. We also have Kirchhoff's voltage law, which applies around any series loop. And yeah, basically conventional current is positive to the negative. That's something to remember. And any current going the other way is considered negative. So conventional current travels from the positive end to the negative end. And Kirchhoff's current law states that the net current is equal to, or the change in current is equal to 0. And Kirchhoff's voltage law says the change in voltage is equal to, sigma voltage is equal to 0. And the positive in a circuit is defined at either point, which is pointing towards the junction or pointing away. So positive is defined either pointing towards the junction or pointing away from the junction. And this is what a node is. So Kirchhoff's current law applies at a node or a junction, and this is what the node is. So the node is that point where the thing just splits apart, basically. That's what the node is. So these are Kirchhoff's laws, parallel series circuits, and how to find resistance for each one of them. Okay, now we can go through magnets. So magnets and magnetic field lines. So ferromagnetic materials are metals including iron, nickel, and cobalt. Basically, they have little domains inside of them that you can change to align in one direction. And when they align in one direction, these domains, they'll become magnetic. So by rubbing a permanent magnet over ferromagnetic materials, we'll align the domains so that we'll have a north pole and a south pole, and we'll make it magnetic basically. And that's what ferromagnetic metals are. Pretty cool for that. And the strength of the force of a magnetic field is denoted by the magnetic field strength and the distance away from the magnetic field we are. So the further away we go from Earth, magnetic field strength stays the same, but the distance increases, and so the strength of the force we experience due to gravity decreases as well. Now let's look at magnetic field lines. So they run from north to south, they never cross, and the closeness of the lines relates to the strength of the magnetic field. We also do right-hand rule for wires and solenoids. So right-hand rule for wires and solenoids. We have, we'll talk about this later, but basically the force generated by the magnetic field lines is given by the palm. So the direction that the palm points in kind of denotes the force that is generated in a magnetic field line. To find the strength of a magnetic field now, we go through this equation. So B, which is the magnetic field, the strength of the magnetic field basically, is given by this constant over here, which is on your data sheet, times current divided by 2 pi r, which is and r is the distance away from the wire. So yeah, because we have a wire here, because current through a wire produces a magnetic field around it. So we do a prac on this later in school, but basically current through a wire produces a magnetic field around it. So if we're trying to find the strength of the magnetic field produced within a current within a wire, we do this equation. B is equal to U0 I divided by 2 pi r, and this is a constant. This is current that's running through the wire, and this is the distance we are away from the wire. And now if we're trying to find the magnetic field strength of coils of wire or solenoids, all we have to do is we have to multiply this equation by n essentially. So we have the length of the solenoid, and now we have the number of turns of the solenoid. So n over L, essentially, this ratio of n to L tells us how tightly packed the solenoid is, and it's called density basically. And the greater that density, the greater the magnetic field strength produced. So that's wires and magnets, and that's how the strength, or like the magnetic field strength within coils of wire or solenoids. And with that, we come through the end of module 4. So I know module 4 was somewhat rushed, but I think the important thing to take away here is the fact that you understand these equations and the variables within these equations, so that if you do ever need to apply them, it's quite easy for you to apply them. And just these rules, they're not too hard to remember. Always north to south, just like how in electric field lines, they're positive to negative. They never cross the closest lines. Ferromagnetic materials, you will learn through them. You will learn about them in more detail in class, but just know that main thing to do is they have magnetic domains, and if we align the magnetic domains of the atoms in the metal, then we make it magnetic basically. And another important thing for magnetism is Kirchhoff's laws, and also like resistance within a parallel and series circuit, and these formulas for voltage and power. So it's mainly the formulas. I feel like this is pretty. If you think about it, like, if you think about it conceptually, it will be pretty okay to understand this. But yeah, just the main thing to understand is the formulas. Most of them will be on your data sheet, but just understand the variables and what, the definitions for each of them, so you understand how it's made up and how the formula is composed of. So it just makes it a lot easier to apply the formulas. So that's the main top.